Welcome everybody, week 15, day 3. Today we're going to be talking about beautiful computer science. I call it that because there is a class at Berkeley called The Beauty and Joy of Computing. And it is kind of the equivalent of this class over there, and I've stolen some of their stuff for my class. Today what we're going to be talking about are some of the kind of interesting things you can get out of computer science. And we're going to also be talking about problem solving techniques, because that's really what computer science is, right? Like, we think of computer science as like nerds in front of a computer, you know, writing a program. But really what computer science is at its core is problem solving. Like, you're given some sort of problem, and sometimes very straightforward, you know, like that would be something that's pretty straightforward, like you know, build an inventory system for the company you're working at. And so you write a program that allows the manager to, like, maybe you're working for Lithia Nissan or something, and so you write a program and you allow the manager to add cars into stock and to query the database to see what cars you have in stock and to remove cars from stock. And I don't know, it's pretty straightforward and stuff, and maybe that doesn't really require a lot of problem solving. It's just, you know, once you know how to program, like, it's pretty easy and you just do it. But the interesting problems, yeah, they require a lot of thinking. They require smoke to come out of your ears. They require you to really, you know, sketch out answers, and you get sheets of paper and you like kind of sit there and be like, all right, you know, how the hell do I do this, you know? And some people find that fun. Some people hate it. And well, the hard part, I don't know if it's fun for anybody, but when you finish it and you find a solution, like, computer science people in general are like, yes, you know, like, there was this really tricky problem and I managed to do a very clever solution for it. And that's usually the mark of a good computer science person, is that they feel joy and satisfaction at really having overcome a tough problem, right? It's like when people climb Mount Everest, right? They're like, yes, I made it. You know, it's like, for me, I'd rather just you know, see a photo of what it looks like from the top of Mount Everest, then I don't need to put myself through it. You know what I mean? I don't think I would get much satisfaction at you know, dying. So, you know, the attitude that somebody has towards problem solving is one of, you know, sort of the hallmarks of, like, whether or not you'd be a good computer scientist or not. Be able to think logically, being able to think critically, it's very important too. But usually, like, maybe even the most important hallmark is, like, when you're given a problem, like, it kind of excites you a little bit, you know, like, all right, this is interesting, you know, and then when you solve it, it's like, bah, yes, you know, I got it. And so what we're going to be talking about today, again, is problem solving and some approaches. And even if you're not a computer science major, these approaches are applicable to your life, because the problem solving techniques that we use in computer science work in pretty much any STEM field, or, you know, really in real life as well. So we'll talk about that. Okay, so we're going to talk about fractals. We're going to talk about recursion. We're going to talk about divide and conquer. Recursion and divide and conquer problem solving, kind of like ways of thinking about problems and ways of solving problems. And like I said, even if you're not a computer science major, if you think about these things and kind of internalize them, it'll help you no matter what field you go into. You know what I mean? Probably would even help outside of STEM, you know. If you're an artist, well, if you're an artist, the fractals part will probably appeal to you. So fractals are, I don't know if any of you guys have seen Frozen. There's a part during the iconic song of Frozen 1 called Let It Go. And in it, in the I think it's at the start of the bridge of Let It Go, Elsa says, "My soul is spiraling in frozen fractals all around." You haven't heard of it? Let's see if I can do this without getting a copyright strike. Frozen fractals. Oh, look at that. Hey. So there's a lot of consonants and alliteration in Let It Go, by the way. My soul is spiraling in frozen fractals all around. There's a lot of S's, a lot of sibilants in that song. So, okay, so what is a fractal? A fractal is when something exhibits self-similarity, if you want more sibilants. Self-similarity. In other words, if you zoom in really close on something, it looks like that thing when you zoom out. So if you zoom in on a mountain, you zoom in on a pebble, and that pebble looks like a mountain, right? You zoom out, you see a rock. You zoom out, you see a boulder. You zoom out, and you see a mountain, right? That's self-similarity. So when the same object looks similar at different zoomed in scales, that's called a fractal. And guessing you've heard the song a lot. I mean, I may or may not have a kid. So, all right. Let's see if we can do this. The thing about doing this as a programming assignment, actually, in CSI 40. Let's see, Mandelbrot zoom. All right. No audio. So as you zoom in on the Mandelbrot set, you'll see that as you zoom in, the Mandelbrot set resembles itself. Although there's some pretty cool artwork. Look at that. I feel like I should be playing Tool right now. And this is actually just math, and the math behind it is actually pretty simple. If you guys know what a complex number is, you just exponent a complex number, and that's it. The numbers you feed in are the position on the screen. So as you keep zooming in and zooming in and zooming in, you'll see the same kinds of patterns repeating. Tool definitely fits the zoom, yeah. This is so trippy, yeah. Yeah, this is all we're doing today. We're just gonna drop some acid and watch Mandelbrot zooms for 20 minutes. But it's cool, right? Like, you know, and you'll keep seeing these same patterns repeating over and over again. But even still, it's a little bit different, right? Like, we haven't seen this thing here before. If you zoom in more, this kind of looks like the original Mandelbrot set, right? Keep zooming in more and more and more. You see that? If we go back. To there, right? And so it's the self-similarity principle. And if I fast forward 8 minutes of zooming, see this, and it's still different, but you can still keep seeing these same galaxies and things like that. And so some people say, like, you know, an atom resembles a solar system, right? So that would be kind of an example of the self-similarity principle, even though Jupiter doesn't exist as a waveform of possibilities. But, yeah, you just keep zooming and zooming, and does it end? Is there a complex math equation behind it? No, it's not complex at all. It's actually a really simple math equation. Yeah, but eventually you ascend to the celestial heavens and call it a day. Yeah, I can actually show you my my TA for CSI 40 and 41. It's 2 plus 2 equals spirals. I can actually show you the code for it. That's it. That's the whole thing. So basically, you have a complex number. If you know what a complex number is, it's got a real part and an imaginary part. It gets squared over and over again. Actually, it starts at 0, 0. Sorry. So it takes the complex number, adds it in, then it gets squared, then it gets added in, then it gets squared, then it gets added in, over and over again, in this case 20 times. And then it takes the Pythagorean theorem, x1 minus x2 squared, y1 minus y2 squared, and it sees if it's smaller than some radius of 2, apparently. Yeah. And then if the Pythagorean distance of this complex number is less than 2, then returns true. Otherwise, returns false. And that's it. That's the entire thing. And so, if you run this, there it is, right? You guys recognize that? So, you can scroll around. How do we zoom in? S is zoom in, W. Okay. So if we zoom in, I don't know if it's working right now. But yeah, I mean that you can see just that tiny little equation resulted in a really beautiful bit of artwork, right? And that's it. And a lot of these fractals can be made using really simple rules. How's it able to zoom in so close? You pass in the screen location of the current point you're looking at. You pass in the zoom level, and that's part of the equation, basically. That's really it. And so with something so simple, it generates something so complicated. It's really beautiful. For example, let's say that we do the following algorithm here. Start with a line. Chop out the middle third and replace it with a little kink, like a mountain. Like that. You guys understand? So you start with a line, cut into thirds, and the middle third of it, cut it out and put a kind of a mountain in its place. And then repeat. So what do you think it'll look like after the next iteration of this? So for every line, cut out the middle third and replace it with a mountain. What do you guys think it'll look like after the second iteration? Edge of infinity, Mandelbrot fractal zoom. Nice. Maths down. How about that internet speed, huh? It's amazing. Yeah, so what's going to happen is the middle third here is going to have a mountain, and then this chunk here is going to have a mountain, and this one's going to have a mountain, and this one's going to have a mountain. Ooh, that's beautiful. And there's many different kinds of fractals. The Mandelbrot set's, kind of the most famous one. How about that internet? My goodness. Oh. Ooh, that's pretty. That is really pretty. I like their choice of colors here. The other one was nice too. The other one definitely reminded me of Tool more. The third eye reflection. Yeah, it's lagging. All right. So second iteration, you get this. Yep. What do you think it's going to look like after the third iteration? Remember, for every line segment, chop out the middle third, add a mountain. That. Like that. Okay. So you guys see how you can make this really, really complicated artwork using a very, very simple rule. This is the rule. Chop the middle third out and replace it with a, two segments that look like this, right? Iteration 1, iteration 2, iteration 3, iteration 4. You've already got something that is really too complicated for a human to draw, and it looks kind of cool, So this is, in a bit we're going to talk about recursion, but this is an example of recursion. For each of something, do something within it, and then you go in, and then repeat within that, right? So before we had one line, now we've got 4 lines, all right? So each of those 4 lines do this. Now we've got 4, 12, 16, 20 lines or something. No, wait, 16 lines. And so for each of those 16 line segments, do it again. Bloop. And for each of those, do it again. And so using very, very simple rules, we can create very complicated behavior. Like if I had started from this and didn't tell you how it was made, right? Like, how would you guys go about drawing this? You'd be like, I don't know. And if you asked me how to go about drawing this, I'd be like, I don't know. You know what I mean? Like, if you start on the complicated side of things, then it looks like it's just impossible, right? And if you told somebody who started with this that, it's a very simple thing to draw, but Kuso, no way, but yeah, I mean, do you guys get what I'm getting at here? Like, you can have something that's very, very simple generate things that are very, very complicated. And so some of the most interesting algorithms in computer science, which seem impossible, turn out to be like this. Like, after you understand how they work, you're like, oh wow, that's actually really simple. Like, huh. I would have thought this would have been millions of lines of code to do, right? No, but with the Mandelbrot set, you do repeated squaring of a complex number and then adding the original complex number in. So it's basically doing x squared plus x over and over again. And kind of, yeah. The previous iteration is squared plus the original number. So it's not, it's a better way of putting it. So the previous iteration squared plus the original number. And then you take that, previous iteration squared plus the original number. You just keep doing that over and over again. And then see if the result you get is, you take the Pythagorean theorem on the complex number and see if it's less than 2 from the origin. And that's it. And that generates that incredibly complicated and beautiful thing. It's a very simple algorithm, right? Math is beautiful. Can be. Not always. I will point out again that math terminology is not always that beautiful. Yeah. X-Men hat. No. This is not at all what I'm looking for. Free Fortnite. It's amazing. Yeah. Like, yeah. Matt, for some reason, like, I don't know, they can't just like make a new variable. It's got to be like, you got x bar, you got x prime, x hat, x tilde, like, it's just got to be x, dude. I don't know why. It just has to be x. And then you can combine that with subscripts. X hat 0, X hat 1, like, could you call it, I don't know, something not X? No, must be X. But math can be really beautiful. When I was a kid, we did a Pascal's triangle. You guys know what Pascal's triangle is? Um, this thing? Yeah, Blaise Pascal, famous dude, um, made this, and each number is just the sum of the people, kind of northwest and northeast of it, and so what we did was we colored it. We had this on like some sort of like graph paper, but it was like diamond graph paper, I guess. So like the graph paper kind of looked like this. You filled it in one and one, two, one, and then we colored it based on if the numbers were divisible by 2, divisible by 3, divisible by 5, and it generated these really beautiful like snowflake colors. It created these really complicated patterns and things like that. I was like, dang, dude, and it's just addition, right? Like I think in middle school at the time, and you just do addition, and then you just check to see like if this number is divisible by 3. All right, color it green, and this one's divisible by 2, so color it blue, and this one's divisible by 5, and 5, and 5, and 5, and so those get red or whatever, and it generated these really cool, really neat patterns. And somewhere I think I've still got it actually because I thought it was neat, And again, like if somebody just handed you the snowflake pattern and was like, figure out how I made this, you'd be like, I don't know, dude. Like, it's baffling. So a lot of computer science and a lot of life is like that, where there's actually a really beautiful and simple problem that through the powers of recursion, the self-similarity property, you can come up with a really clever solution. So here's the same thing in 2D. Oops, and it's animated GIF, so I can't pause this. Do you guys see how that works? So for every line, you take out the middle third and put a little mountain on there. So you're showing off some Mandelbrot action. Yeah, Muya here is the guy that made that code. So why doesn't it work when I zoom in, Muya?
You weren't zooming in the right place. If you zoom into the middle of the Mandelbrot set, there's nothing there.
Gotcha.
Or that's all of the things that are in the Mandelbrot set. Where it gets interesting is on the edges of that. But if you're going to show it, use the link I just sent on GitHub. Clone that, because that's this is just for the assignment. I've done a lot more work on it on my GitHub version. Like, that's just the I coded this in 5 minutes version.
Gotcha. Right. Do you have a copy of it on the server?
I mean, you could just clone it real quick. I sent the link in the chat.
Copy link. Okay. Git clone. Git G. Git. I'm typing through some serious lag here. Git clone. My wife is streaming 4K. My daughter's on Zoom. I'm streaming this on YouTube and on Discord. Yeah. Alright, so cd into console fractaler. Alright, make. Alright.
Yeah, so if you can obviously zoom in with WNS, and then if you hit A or D, or yeah, A or D. D increases the amount of iterations it does, which makes the resolution of like how accurate it is. It increases how accurate it is. So if you're zooming in, you'll eventually reach a point where everything's just the same. But if you hold down D and increase the iterations, it'll get better. But obviously, since the Wi-Fi is, or since the connection's so slow, I'm not gonna be as good.
Okay. I'll play with that. Yeah, that's cool. So please, everybody, give a clap emoji for Muya having done that. So I think it's pretty cool. Yeah, it's neat. This also isn't the class that he's TAing, and he's popping in to tell you guys about it. So.
I noticed it on YouTube when I woke up.
All right, so yeah, all right, and if we zoom in on it, all right, this. Have you heard of the Koch? I don't know how it's pronounced. I've heard different Koch brothers. Yeah, but like Christoph Koch, I think, the famous neuroscientist. I don't think he pronounced it Koch. Yeah. Yeah, so you can see as we zoom in on the snowflake, you just keep zooming in, and it's like an infinite tunnel kind of thing. Yeah, so the rule for the Koch, I don't know, I'm just gonna go with one. The Koch snowflake is you just you start with a line segment or something, you take out the middle third and replace it with 2 line segments like this. That's it, and then you repeat. You see that?
Yeah, I've seen this before. It's pretty cool.
Yeah, and so.
What about the Sierpinski triangle, though?
Oh, yeah, that's a good one too.
That one you can make in MS Paint. Like, there's actually a way to create the Sierpinski triangle just using MS Paint.
Mm-hmm.
It's pretty cool.
I did not know that. That is neat. Sierpinski triangle. I like how YouTube was recommending my own stream to me. That was amusing. Chaos game, fractals emerging from chaos. All right. So, start with the triangle, and then with a few simple steps that doctors hate. A few simple steps that. It's interesting. So that's actually
okay. That's impressive.
Yeah, that's a completely different method. That's just randomly rolling, and it's
yeah.
Huh.
That's actually really cool.
Yeah. Huh. That is super neat. Not what I was expecting though.
Yeah, normally you just draw a triangle and then put 2 more triangles over it.
And then subdivide it, yeah.
Oh, and then here's the carpet. Sierpinski carpet. Oh, but it doesn't create this.
The Triforce. I feel like if we allow this to complete, the gateway to hell will open up. Okay. Yeah. And so recursion is the general term we use for solutions that exhibit self-similarity. So do you guys understand what I mean by self-similarity now? Like, as you zoom in on the Koch, whatever, snowflake, as you zoom in, you notice how the closer you zoom in, it still looks like the zoomed out version, right? Do you guys understand what I mean by the self-similarity principle? You know, if you zoom in on like this, just focus on this line here, you see it's the exact same thing that we had before, like this, right? If you just focus on this one, it's the same. It's the same, right? And if you were to focus just on this line here, you see that you get the same thing. And if you focus on this one here, or that one there, or that one there, or that one there, you get the same answer over and over again. The small scale solution resembles the big scale solution. And anytime you have a problem, here's the big think for today. Anytime you have a problem where the small scale solution resembles the big scale solution, there's probably some sort of recursive solution for it. So there's probably some beautiful and simple way of solving the problem. Okay? So for example, let's give you a real problem from computer science. So let's say you want to navigate from San Diego to New York, right? There's a lot of different routes you can take. If you're trying to go from Balboa Park in San Diego to Central Park in New York, there is a lot of ways you can go. You can go up to Seattle, go through Canada, drop down into Maine, go west to Omaha, right? Then finally make your way to New York. There's, you know, almost an infinite number of ways. You know, you can't try them all. So, so you start thinking about it, you know, and you say, hey, you know, is the Marble Marcher nice? You know, if you think about it, it's like, is the solution at the small scale kind of the same as the solution at the big scale? So like the big scale would be like San Diego to New York. There's tons of roads, tons of intersections. There's freeways and traffic lights and all, hugely complicated. But think about this. Like, you're presumably at your house right now. I don't know. Maybe some of you guys are at Taco Bell. I remember last year when the pandemic started, students like, I can't answer you right now. I'm at the drive-thru at Taco Bell. But like, let's say you're at your house right now, and you just want to go to, I don't know, the nearest elementary school, right? That's a lot easier. You know what I mean? And so that would be, I don't know, maybe you live right across the street, and then it's like, I'm going to walk across the street. But do you guys see how that problem, the solution of finding the fastest route from your house or apartment to the local elementary school, do you guys see how that resembles the same problem at the bigger scale? And if you break it down even more, like, can you find the fastest route from your house to the nearest intersection, right? Then thankfully Google solves that problem. Yeah, well, I'm talking about how Google solved it, right? So somebody at Google had to program this, you know, and at first it looks like an almost impossible task, right? Like, how do you try every route between San Diego to New York? And so what you do is you sort of mentally zoom in on the problem, right? And zoom in and be like, all right, what would it take to navigate from here to the nearest elementary school? And because that problem resembles the big problem, and if you zoom in even further, how do I navigate from my house to the nearest intersection? You know, maybe it's a straight line, maybe there's just two options. Which in my case, yeah, there's really only two options. Yeah, you solve this in CSI 26. Oh, this is Fresno State, so they call it CSI 60. Because it exhibits the self-similarity principle, it's actually possible to solve this very, very easily. And it doesn't seem like it should be easy, but it is. And in fact, you can solve the entire map in America if you want it. You could actually write down what is the shortest path from every intersection in America to every intersection in America. Now, that would take a lot of storage space to actually write all of those down, but Google's got storage space, all right? So it's quite possible they have it solved. Like, they can actually, it's like when you go to maps.google.com and I say, somebody give me an intersection here in Fresno. Shaw and Marks. Okay. So here is Shaw and Marks, and we're going to do directions from Shaw and Marks to Central Park in New York. There it is. Oh, this is on public transit. That's amusing. No, let's do it by driving. Should be easier. So it takes 3 days if you're going to take public transit. If you're going to drive, it is 43 hours. And it gives you a couple different alternate routes. It shows you where there's construction along the way. Obviously, these can't be pre-computed. There's an accident in Oklahoma City, it looks like. Crash. Yeah. So, yeah. Like, it did not have to go through every single possible road. In fact, it's probably just pre-computed. Or at least the big scale stuff could be pre-computed. But they even like take care of like construction and accidents and local traffic and things like that. So they can't fully pre-compute the thing. So yeah, road trip, right? 43 hours. Like I always have students like, yeah, I can't do the homework assignment. I'm on the road. It's like, you're clearly contacting me on internet. Yeah, you do Flappy Bird from Indiana. Like there's no geographical restriction on this. Yeah, I'm snowed in Michigan. I can't do the homework. All on the internet, dude. Like you know. Right. So you guys understand? And so the same algorithm that you use to navigate from, let's say you're going to go from Sean Marks to Dakota and Maroa. Same algorithm, right? Because it's the same problem at the small scale and the medium scale and the big scale, you can actually just write one very simple algorithm to solve it, right? Again, this isn't, we're ignoring things like traffic and, you know, accidents and construction and stuff like that. Just the simplest level, you know, it's just finding the shortest path. And so, you know, finding the shortest path between this intersection and this intersection, right? It's the same algorithm. And so you zoom out and you've got this one. You zoom out, maybe you're going from here to Bakersfield, and you zoom out, and maybe you're going from here to San Diego, and you zoom out, and maybe you're going from Fresno to Oklahoma City. You zoom out, Fresno to New York. Same algorithm. You don't actually have to write a different algorithm for any of it. And so it's a very, very complicated problem. If you think about it at the big scale, it seems very, very complicated. But at the small scale, all you do is just say, what is the shortest path from point A to point B, and you write that down. And then when you do point C, you just use what you'd written down for point A to point B. Is basically how it works, right? So you solve all the small problems, and then you zoom out one level, and you solve all the slightly bigger problems. You zoom out, and you solve all. Because if you know the shortest path from, like, let's say, here's California. Right? SD, Orange County, LA, Bakersfield, sorry, not Bakersfield, that'd be San Bernardino, Bakersfield, Fresno, San Francisco, Sacramento, and the rest of California doesn't count. Because that's how we think of it, right? Like, think of San Francisco, Sacramento, and that's it for California, ignoring the fact that it's a huge amount of land north of there, right? Okay, so like if you had to figure out the fastest route from San Diego to Sacramento, you'd have to try all these different possible routes, and it gets really complicated. But if you know the shortest distance from San Diego to Orange County, which is San Diego to Orange County, you can zoom out one level and solve the shortest route between San Diego and LA. You zoom out and, all right, what's the shortest route from San Diego to Bakersfield? Well, it'd be this way, and you just keep zooming out and using the results of your previous computation, and pretty soon you can actually have a fast route from San Diego to Sacramento without really killing yourself. And yeah, I mean, kind of the way that humans navigate is that way, right? Like if you had to navigate from Sacramento to San Diego, you'd be like, all right, how do I navigate from Sac to Fresno, Fresno to Bakersfield, Bakersfield to LA, LA to San Diego, and maybe you'll try a couple different routes. Like we could take the 5, or we can take the 15. 5's over here, the 15 is over here. By saying the 5 and the 15, you know that I'm from Southern California, because it is the I-5 and it is the I-15 local dialect. Does that make sense to you guys? You don't need to actually solve it right now. Like I said, that's more third semester computer science, actually programming a solution to it. But the program is not very big and complicated, really. You might need a lot of hard drive space if you've got a really big map and you want to write them all down. You'll probably need a good chunk of hard drive space. Let's see, how much would we need? How many street intersections are in America? 1 million intersections. So you need 1 million squared, which is 1 trillion. And if you might need, I don't know, on average 10 steps. So it'd be like, I don't know, just spitballing like maybe 10 terabytes of data, something like that. So less than there is in my PC right now, right? So not too bad. Not too bad. It's a lot, but it's not too bad. And that's for all of America. Okay, so how about this? How about like checkmating? Like, have you guys watched like The Queen's Gambit? It's about a girl who does drugs and dreams about chess. Right? So if you want to checkmate somebody, what that means is they've got their king somewhere on the board. So you got a rook here. This is like the enemy king, whether it's white or black doesn't really matter. And so your rook can threaten squares horizontally and vertically, and so the king would be able to move, either of these ways. And so, for example, if you had a rook here, you could move the rook to the top row here, and then that would checkmate the king, right? And so you can start off with the simplest possible checkmate problem, and then solve it, and then zoom out. And by zooming out, I mean things like, let's add another piece, right? Like maybe white's got a pawn here, right? And so you solve the very smallest. You add a piece and you solve that. You add a piece and you solve that. And the trouble is, like, there could be a lot of pieces, right? And so it quickly becomes unmanageable. But for 3-move checkmates, 4-move checkmates, like each time it gets exponentially harder to solve and write them all down. But you can basically have a chess program that can see checkmate in 4 or 5 moves. That's doable. And so just the limit is your processing power, right? You can just sit there and solve every board position for a king and a queen and a bishop or something, right? Queen here, bishop moves here, king moves here, right? Like, but you start off with just the very simplest, very smallest solution, and then you gradually add complexity to it, and you just keep writing down all of your results. Okay? So, chess is right. Chess gets exponentially more hard as you add pieces to it, but you still have enough processing power these days to do mate in 4, or whatever. How many different ways are there to add natural numbers to get 99? Do you guys see what I mean? Do you know what a natural number is? Natural number would be 1, 2, 3, 4. Sometimes 0 is included, but we're not counting that today because that would make it infinite, right? 0 plus 0 plus 0 plus 0 plus 0. Not counting 0. So how many different ways are there to add the natural numbers up to get 99? You guys see, like maybe this thing is applicable outside of computer science, right? But this would be a good computer science program, I think. How would you program this? Or if you were in a math class, how would you figure this? 98 different ways? Is it? I don't know. So if you think about it at the big scale, it's hard. So start at the small scale. Do you guys understand? I'm trying to teach you guys mental habits of mind that will carry you in any field, right? If you're given a big, complicated problem, like you're way up here, and you're like, how many different ways are there of adding up to 99? You might just start going like, all right, 44 plus 55 and 43 plus 56, and all right, I guess there's 99. But then somebody goes like, wait, what about 22 plus 22 plus 55? And you're like, oh wait, you can have 3 numbers. Oh shoot, this is complicated. You know what I mean? All right. And so the approach that we can take for that is something called divide and conquer. Divide and conquer is the notion you start with the smallest problem possible, and then you use the smaller results to solve a bigger problem. So you start with something like, how many different ways can I add up the number 1? Right? How many different ways can I add up the number 1? 1. Right? No 0, Kenji. Just the numbers available are the natural numbers. Right? So how many different ways can I add up the number 1? For 1, it is 1 way. How many different ways can I add up the number 2? There's 2, and there's 1 plus 1. There's 2 ways. How many different ways can I add up the number 3? Well, I could take the number 2 and add 1 to it, or I could take the number 3, right? So, but how many different ways are there of making 2? There's 2 different ways. So it's not 2 ways of making 3, right? It's not 2 ways of making 3. It's the number of ways of making 2, because I could go 1 plus 1 plus 1, right? But that's the number 2. So I could either add 2 plus 1, or I could take 3. And so the number of ways of getting 2 is 2, so there's actually 3 ways of doing that. And then for 4, I can, and so you use the results of the previous entries to know how many different, you're getting to like, when you're getting down to like, I don't know, 51 or something. It's like, well, I can just do 51. That's one way. Or I can, take 50 and, however many different ways there was of doing that and add 1 to it, And so you use the results of the previous computation. How many different ways are there of making 50? Okay, well, I can add 1 to that, right? How many different ways are there of doing 49? I can add 2 to that. Yeah. And so you use the results of the previous computation to solve the bigger one. And by doing it that way, you can actually figure out the answer to this. Okay. So a really hard problem, when you look at it from the sky, how many different ways are there of adding up 99? You can start just 2 plus 97. You just start like coming up with things like, I don't know, like 10 plus 89, or wait, but 10 could be 5 plus 5 plus 89. You just start, it's like, I don't know, it's too complicated. Like you get overwhelmed, right? But when you start by being like, all right, how many different ways are there of adding up 1? There's 1. That's easy, right? And then how many different ways are there of doing 2? That's easy. And you start with the easy things, and then as you go up the numbers, you use the results of the previous computations to solve the bigger computations. And when you do that, it's actually not too bad. Actually not too bad. Okay. And this applies across all math and science disciplines, probably outside of STEM as well, right? Like, if you're an auto mechanic, you need to rebuild a car. You don't just like stare at the entire car and be like, I don't know where to begin. You start with a small problem, right? Like I'm going to start by pulling the engine out, and you start, you hoist it and work on the things that tie it in and pull it out, and then all right, I'm gonna, you start small and you work your way to bigger and bigger things, and this is a problem solving technique we use all the time in computer science. That if you learn it, even if you're not a computer science major, it'll really help you in life. Okay, so if you're a math major, then it'll help you. Divide and conquer is very useful in math. If you're a chemist, and you have to do flow chemistry. Flow chemistry is when, rather than starting with a batch of reagents and doing a batch and making whatever product you want, you have like things dripping together in a tube, and it's just constantly making product. And so if you're going to build this whole assembly line for chemicals, it can be overwhelming. And so you start small, like, all right, how are we going to make this? And then you work your way up. Okay. Would it be inductive reasoning? Yeah. So this would very much be inductive reasoning, right? Use a proof by induction. In fact, it's not exactly inductive reasoning because it's not based on past experience. We're making a prediction about the future. Instead, it's called proof by induction, and that's actually provable. It's actually deductive reasoning, I guess, because you can prove it. You can prove it to be true. You start with some starting premises, and you can actually prove that this solution follows this pattern. You can prove it mathematically. You can deduce from the starting axioms of mathematics the rule for this and get an answer. You can prove that deductively, okay, even though it's a proof by induction. So useful for dealing with problems in life. If you're some major event happens, you have to sit there and break it down, break the problem down, break it down as small as you can. Work on those small problems, and then work up from there. Okay. So that is it for today, guys. I hope maybe some of you guys that are not computer science majors are maybe inspired to be computer science majors, and if not, then hopefully you guys all learned an approach for solving problems that will be useful for you. So, I think the computer science is useful outside of computer science, because it really is just a mental discipline, and the mental skills you learn from computer science help you just across the board in life. That is it for today, guys. Have a great weekend. Your capstone essays are due on Monday, so make sure you guys get those. It's a big chunk of your grade. Okay. And if you have any questions, please post on Discord, and I will get to them.